Look up at the night sky, and what do you see? A vast, endless darkness stretching beyond imagination, dotted with distant stars. It's easy to assume that the blackness between those points of light is just nothing. Empty space, a true void. But what if I told you that this emptiness is one of the greatest illusions of the universe, that what we perceive as nothing is actually a seething, bubbling sea of hidden activity, governed by laws so strange they defy common sense? This isn't science fiction, it's the cutting edge of modern physics, and it's about to change the way you see the cosmos forever. Think about the word nothing. It feels absolute, final, but in the depths of space, nothing doesn't exist. Instead, the void is alive with quantum fluctuations, particles popping in and out of existence so fast they evade detection. It's filled with dark energy, an invisible force pushing the universe apart at an accelerating rate. Even the vacuum itself crackles with potential, a cosmic stage where the laws of physics play out in ways that seem almost magical. How can emptiness be so full? That's the paradox we're diving into today. This journey will take us from the mind-bending principles of quantum mechanics to the frontiers of cosmology, where scientists are still grappling with the true nature of the void. We'll explore how empty space might hold the key to understanding dark energy, why quantum particles refuse to sit still, and what all of this means for the fate of the universe itself. By the end, you won't just see the night sky differently, you'll feel it. That darkness isn't passive. It's dynamic, mysterious, and far stranger than we ever imagined. So let's begin where all great cosmic questions start, by staring into the abyss and discovering that it stares back. For centuries, the greatest minds in astronomy gazed at the night sky and saw emptiness. When Galileo first turned his telescope upward, he mapped stars and planets but described the space between them as a perfect void. Even Einstein, in his early work, treated the cosmos as a static stage, a backdrop where celestial objects moved through pure nothingness. But here's the twist, every one of them was wrong. The universe doesn't do emptiness. What we call space is more like an invisible ocean, churning with forces we're only beginning to understand. Take the quantum vacuum, for example. At scales so small they defy imagination, particles and antiparticles erupt into existence, collide, and vanish again in less time than it takes light to cross an atom. This isn't metaphor, it's measurable physics. Scientists call it quantum foam, and it means even the darkest patch of space is a frenzy of creation and destruction. Imagine blowing soap bubbles in a cosmic bathtub, each one a temporary universe obeying its own rules before popping back into the void. That's the reality of so-called empty space. Then there's dark energy, the ghostly push behind the universe's accelerating expansion. Picture inflating a balloon with invisible ink. You can't see what's stretching the fabric of space, but the effect is undeniable. Galaxies race away from each other faster than gravity should allow, as if the void itself is generating repulsive force. Early astronomers couldn't have dreamed of such a phenomenon. Their nothing is actually the most dominant component of the cosmos, making up nearly 70% of all existence. What's truly humbling is how recently we've uncovered these truths. The quantum vacuum wasn't confirmed until the late 20th century, and dark energy was only discovered in 1998. For millennia, humanity underestimated the void because we couldn't perceive its hidden machinery. Now we know better. The greatest lesson when it comes to the universe, nothing is just a word waiting to be redefined. If you could shrink down to the size of an atom and peer into the deepest void of space, you wouldn't find stillness, you'd witness chaos. Quantum fluctuations turn the vacuum into a cosmic dance floor, where particles and their antimatter twins materialize, pirouette, and vanish in less time than it takes to blink. These aren't just theoretical quirks, they're the universe's heartbeat, pulsing beneath the surface of what we call empty. Consider this: at every cubic centimeter of space, no matter how seemingly barren, crackles with energy. Virtual particles, electrons, quarks, even entire atoms borrow energy from the void, exist for a fleeting moment, then repay their debt by disappearing again. It's like the universe has a strict no free lunch policy, but with a loophole: as long as the books balance instantly, anything can happen. This isn't magic, it's Heisenberg's uncertainty principle in action, proving that at quantum scales, even nothingness refuses to sit still. These fluctuations aren't just cosmic background noise, they shape reality. When two uncharged metal plates are placed impossibly close in a vacuum, quantum forces push them together. It's called the Casimir Effect, and it's like trying to clap in a room where invisible hands keep slamming your palms together. Why? Because the space between the plates can't sustain the same particle frenzy as the space outside, creating a pressure differential that defies classical physics. But the real mind bender: these fleeting particles might hold the key to spacetime itself. Some theories suggest that without quantum fluctuations, the fabric of the universe would lack the tension needed to support matter. Picture a trampoline with no springs. It's the constant buzz of virtual particles that gives the cosmos its structure, like invisible threads weaving the tapestry of reality. Even black holes, the universe's ultimate voids, leak radiation thanks to quantum activity at their edges, proving that no corner of existence is ever truly silent. So the next time you gaze at the night sky, remember that darkness isn't dormant. It's a hive of potential where particles flicker like fireflies in the cosmic night. What we call empty is simply the universe's way of hiding its most vibrant secrets in plain sight. Dark energy is the universe's greatest magic trick, an invisible hand stretching the cosmos apart, faster and faster, with no strings attached. Imagine blowing up a balloon with a mind of its own, one that inflates more violently the bigger it gets. That's what's happening to our universe right now. Galaxies aren't just drifting apart, they're being pushed by something we can't see, don't fully understand, and yet dominates nearly 70% of everything that exists. Here's the mystery: Einstein's equations originally suggested space could have an inherent energy, a sort of background tension he called the cosmological constant. He later dismissed it as his greatest blunder, but modern astronomers think he might have been right all along. Dark energy behaves exactly like that constant, a property woven into the fabric of space itself. Every cubic centimeter of nothingness, no matter how empty, could be brimming with this repulsive force, growing stronger as the universe expands. The evidence is staggering. When scientists measured distant supernova in the late 1990s, they expected to find the universe's expansion slowing down, pulled by gravity's relentless tug. Instead, they discovered the opposite. The light from these exploding stars was fainter than it should be, as if space had stretched even more than predicted during their journey to Earth. It was like throwing a ball upward only to watch it accelerate into the sky, defying gravity's grasp. What makes dark energy so unsettling is its timing. For billions of years, gravity ruled the cosmos, drawing matter together into galaxies and clusters. But around 5 billion years ago, dark energy took over. Now, it's as if the void is fighting back, pushing galaxies apart so fiercely that someday, distant civilizations might look up and see nothing but blackness. Their cosmic neighbors vanished beyond an unreachable horizon. Theories abound. Some suggest dark energy is a new kind of field, like an invisible version of magnetism permeating space. Others propose it's a sign of extra dimensions leaking gravity away from our universe. But the most radical idea, that we're witnessing the birth of entirely new physics, a clue that Einstein's relativity, while brilliant, is incomplete. One thing's certain, dark energy forces us to confront how little we truly know. The vast cosmic voids we once wrote off as empty aren't just passive gaps, they're the universe's engine rooms, humming with a force that's rewriting destiny itself. And the more we learn, the clearer it becomes. The greatest mysteries aren't in the stars, but in the seemingly nothing between them. Dark matter is the universe's silent architect, an invisible hand sculpting galaxies into existence while leaving no trace of itself. If dark energy is the force pushing the cosmos apart, dark matter is the glue holding it together, a cosmic scaffolding hidden in plain sight. We can't see it, touch it, or even detect it directly, yet its gravitational fingerprint is everywhere. Look at a spiral galaxy spinning like a celestial pinwheel, and you'll notice something strange. The outer stars whirl just as fast as those near the center, defying the laws of motion. According to Newton, those outer stars should be flung into space unless something unseen, something massive, is anchoring them in place. This paradox first emerged in the 1930s when astronomer Fritz Zwicky noticed galaxies in clusters moving too quickly to be held by visible matter alone. He called the missing ingredient Dunkel Materie, dark matter, a placeholder for a mystery we're still unraveling. Today, we know it makes up roughly 27% of the universe, 5 times more than all the stars, planets, and gas combined. Imagine building a house where 80% of the framework is made of a material you can't see or measure, yet without it, the entire structure would collapse. That's the role dark matter plays on a cosmic scale. The evidence is etched into the fabric of space itself. When light from distant galaxies passes through massive galaxy clusters, it bends like a straw in a glass, a phenomenon called gravitational lensing. But the distortion is far stronger than visible matter can explain, as if invisible lenses are magnifying the light. Maps of the cosmic microwave background, the afterglow of the Big Bang, show ripples where dark matter's gravity sculpted the early universe. Even the way galaxies are distributed strung along vast, web-like filaments points to an unseen framework guiding their placement. What is it? Theories range from exotic particles like WIMP, weakly interacting massive particles that barely interact with normal matter, to primordial black holes formed in the universe's first seconds. Some scientists speculate it could be evidence of extra dimensions or even a flaw in our understanding of gravity itself. But here's the tantalizing truth. Every time we think we've cornered dark matter, it slips away. Detectors buried deep underground, shielded from cosmic noise, wait for a single collision between a dark matter particle and ordinary atoms. Space telescopes scan for gamma rays that might betray its presence. So far, the void keeps its secrets, yet without dark matter, the cosmos as we know it wouldn't exist. It's the reason galaxies formed so quickly after the Big Bang, their seeds nurtured by dark matter's gravitational wells. It's why the universe isn't a diffuse soup of gas but a tapestry of light and structure. And perhaps most hauntingly, it's a reminder that 95% of reality is made of stuff we can't perceive. Dark matter and dark energy, twin enigmas rewriting the story of existence. The next time you see a galaxy glowing in a telescope, remember, you're not just looking at stars, you're seeing the shadow of something far greater, a hidden universe waiting to be decoded. One of the most jaw-dropping demonstrations that nothing isn't passive comes from a lab experiment so precise it feels like magic. Picture 2 ultra-smooth metal plates placed barely a hair's width apart in a perfect vacuum. No atoms, no light, just empty space. According to classical physics, nothing should happen, but in reality, the plates snap together as if pulled by invisible strings. This is the Casimir Effect, where the void itself pushes back with measurable force, proving that emptiness is anything but weak. What's happening between those plates reveals quantum physics' strangest truth. Normally, space buzzes with virtual particles appearing and vanishing in a chaotic dance. But when the plates are brought extremely close, only certain wavelengths of these fluctuations can fit between them, like trying to play a full orchestra in a tiny closet. Outside the plates, particle waves of all sizes continue their frenzy, creating a pressure imbalance that literally crushes the plates together. It's not suction, it's the universe itself pressing in from the edges where the quantum party never stops. The implications shatter our everyday intuition. We think of forces as coming from tangible things, magnets, gravity, or springs. Yet here, pure nothingness generates enough push to move physical objects. Modern experiments measure this force at distances smaller than a virus, where the Casimir effect becomes dominant. Some engineers even worry about its impact on microscopic machines, where phantom quantum forces could cause gears to stick unexpectedly. But the real revolution is philosophical. For centuries, we've imagined space as an empty stage. The Casimir effect proves the stage itself is an active participant, its energy capable of real work. Some theorists speculate this quantum pressure might have played a role in the early universe, helping shape the first structures in existence. Others wonder if we could someday harness vacuum energy itself, though the challenges are as vast as space. Perhaps most mind-bending is what this says about reality's texture. Those virtual particles aren't just mathematical tricks. Their absence creates measurable effects, like musical notes missing from a symphony. The silence between them has weight, so next time you see two surfaces clinging inexplicably like a gecko's foot or smartphone screen protector, remember, it might not be glue. It could be the universe's invisible quantum handshake where nothingness reaches out and grabs hold. Even at absolute zero, the coldest possible temperature where all molecular motion should cease, the universe refuses to sit still. Quantum mechanics reveals a startling truth. The void isn't just active, it's brimming with infinite energy. This is zero-point energy, the baseline hum of existence, where particles flicker in and out of being even in the absence of heat, light, or matter. It's as if the cosmos has a floor you can't fall below, a seething undercurrent that makes true nothingness impossible. The numbers behind this energy are staggering. Calculations suggest a single cubic centimeter of empty space contains enough zero-point energy to boil all the oceans on Earth. Yet here's the paradox: this energy is locked away, inaccessible under normal circumstances. It's like living atop an ocean of oil but lacking the drill to reach it. This hasn't stopped scientists and engineers from dreaming. Some theorize that if we could tap even a fraction of this energy, it could revolutionize propulsion, enabling spacecraft to cross interstellar distances without fuel. Imagine an engine that pushes against the quantum vacuum itself, harnessing the universe's own restless energy to propel us forward. But zero-point energy isn't just a futuristic power source, it's a window into reality's deepest layers. The energy isn't random, it follows precise quantum rules dictating how particles behave at microscopic scales. Without it, atoms wouldn't hold their shape. Electrons would collapse into their nuclei, and chemistry as we know it would vanish. This so-called empty energy is what gives structure to everything, from the crystals in your watch to the DNA in your cells. The implications stretch beyond engineering. Some cosmologists speculate that zero-point energy might be the origin of dark energy, driving the universe's accelerating expansion. Others wonder if it could explain the cosmological constant Einstein's greatest blunder that turned out to predict the energy of empty space. Even black holes, those cosmic vacuum cleaners, might owe their terrifying properties to quantum fluctuations at their event horizons, where zero-point energy becomes so intense it radiates particles back into the universe. Of course, there are skeptics. Extracting usable energy from the vacuum remains a monumental challenge, with many physicists comparing it to trying to power a city by catching individual raindrops. The energy is everywhere, but it's also perfectly balanced, canceling itself out unless manipulated in ways we don't yet understand. Yet history shows that today's impossibilities often become tomorrow's breakthroughs. The same quantum principles that once seemed esoteric now power your smartphone and MRI machine. What's undeniable is this: zero-point energy forces us to rethink the very meaning of nothing. The void isn't a barren wasteland, it's a reservoir of potential, a cosmic battery waiting to be understood. Whether it fuels starships or simply deepens our grasp of reality, one thing's clear: the universe leaves no room for emptiness. Even in the deepest cold of space, the show never stops. Imagine the universe as a frozen lake on a winter morning, seemingly still, but hiding an unstable truth beneath its surface. What if the vacuum of space isn't truly empty, just trapped in a fragile state? This is the spine-chilling premise of vacuum decay, a theory suggesting our universe could be sitting on a cosmic tightrope, one misstep away from annihilation. Here's how it works. The laws of physics depend on something called the Higgs field, an invisible energy network that gives particles their mass. Right now, this field exists in what scientists call a false vacuum, a stable but not perfectly stable state. Think of it like a marble resting in a shallow bowl. It's not moving, but with enough energy, it could roll into a deeper valley, a true vacuum where the rules of reality would rewrite themselves. In vacuum decay, a quantum fluctuation could kick that marble over the edge, creating a bubble of true vacuum that expands at the speed of light. Inside this bubble, fundamental constants like the speed of light or the strength of gravity might change instantly. Atoms could unravel, stars dissolve, and the universe as we know it would cease to exist, not with a bang, but with a silent, irreversible shift. The worst part: we wouldn't see it coming. The bubble's edge would move faster than light, giving no warning before it reached us. This isn't just speculative horror. The math checks out. In 1982, physicist Sidney Coleman calculated how such a bubble could form, showing that our universe's current state might be metastable, a temporary pause before catastrophe. Some theories even suggest vacuum decay could have already begun somewhere in the cosmos, its wave of destruction racing toward us unseen. Yet there's a strange comfort in this existential threat. If vacuum decay is possible, it's also vanishingly unlikely. The universe has persisted for 13.8 billion years without collapsing, suggesting our false vacuum is incredibly durable. Plus, if a bubble did form, it might not destroy everything. Some models propose new physics inside could spawn fresh universes, turning doomsday into a cosmic rebirth. So while vacuum decay remains one of physics' most unsettling ideas, it also highlights an astonishing truth: the void isn't just empty space to ignore. It's a dynamic, precarious structure, and our entire reality depends on its delicate balance. The next time you gaze at the night sky, remember, the darkness isn't just hiding stars. It's holding its breath. Black holes are the universe's ultimate paradox regions, where so much is compressed into so little that the very idea of nothing ceases to make sense. Picture a place where gravity wins the cosmic tug-of-war, crushing matter so densely that not even light can escape its grip. But what makes black holes truly bizarre isn't just their power to trap everything, it's how they twist the fabric of space itself into something unrecognizable. At the edge of a black hole lies the event horizon, a point of no return where the laws of physics as we know them start to unravel. Cross this invisible boundary and space and time switch roles. The emptiness we're familiar with becomes a one-way river, flowing inexorably toward the singularity, a point of infinite density where space and time cease to exist entirely. Think of it like a cosmic waterfall. From the outside, the water appears calm, but once you pass the edge, there's no climbing back up. What's even stranger is what happens to the concept of nothingness inside a black hole. In the vacuum of space, we've seen how quantum fluctuations create particles from empty space, but near a black hole's event horizon, these fluctuations get stretched to extremes. Pairs of virtual particles, usually popping in and out of existence together, can get torn apart. One falls into the abyss while the other escapes as radiation. This is Hawking radiation, the slow leak that causes black holes to evaporate over eons. It means even the darkest voids aren't truly static. They're subtly glowing with quantum energy, proving that nothing can still have consequences. Then there's the singularity itself, where gravity becomes so intense that space-time curves into an infinite pinch. Here, our understanding of physics hits a wall. Density reaches a point where matter isn't just compressed, it's erased from existence as we know it. The equations of general relativity break down, screaming for a theory that can marry gravity with quantum mechanics. Some scientists speculate that singularities might be gateways to other universes or loops in time, while others argue they're cosmic dead ends where information vanishes forever. But perhaps the most mind-bending realization is this: black holes don't just warp space, they redefine it. The empty space around them isn't passive. It's a dynamic, churning maelstrom where time slows to a crawl and distances stretch like taffy. A spacecraft orbiting a black hole would experience time far slower than one farther away, as if the void itself were stretching the seconds. Even light, the fastest thing in the universe, gets bent into arcs and rings around the black hole's shadow, creating eerie cosmic mirages. So when we say black holes challenge our understanding of nothingness, we're not exaggerating. They're cosmic laboratories where the rules get rewritten, forcing us to confront the limits of our knowledge. The void inside a black hole isn't just empty, it's a realm where emptiness becomes something else entirely, a place where space and time lose their meaning. And as we peer into these abysses, we're not just studying distant objects, we're glimpsing the edges of reality itself. If black holes are cosmic vacuum cleaners, sucking everything into their inescapable grip, then white holes are their bizarre theoretical twins, universal fire hydrants blasting matter outward at impossible speeds. These hypothetical objects, first proposed as mathematical curiosities in Einstein's equations, flip the script on everything we know about cosmic voids. Where a black hole's event horizon marks a point of no return, a white hole's boundary would be a point of no entry. Nothing gets in, but matter and energy erupt outward relentlessly, as if the universe itself were vomiting starlight. The idea emerges from the strange symmetry of general relativity. Just as the math allows for objects with gravity so strong nothing escapes, it also permits regions where gravity repels so fiercely nothing can approach. Picture a black hole running in reverse. Instead of a swirling drain, it's a geyser shooting particles into space with enough force to outshine galaxies. Some theorists speculate that white holes could be the other end of black holes, connected by wormholes like cosmic subway tunnels where matter enters one station and emerges light years away. Others suggest they might be remnants of the Big Bang itself, primordial pressure valves left over from the birth of spacetime. But here's the catch: no one's ever seen a white hole, and for good reason. Unlike black holes, which form naturally from collapsing stars, white holes would require conditions so extreme they defy known physics. Energy can't just materialize endlessly, it violates the laws of thermodynamics. Yet intriguingly, there are cosmic anomalies that almost fit the bill. Gamma ray bursts, the most violent explosions in the universe, fling energy across billions of light years in seconds, as if something tore open a hole in reality. Even the Big Bang shares eerie similarities with a white hole's behavior, an incomprehensible outpouring of matter from an infinitely dense point, the most radical possibility. White holes could be black holes in disguise. Some quantum gravity models suggest that when a black hole dies by evaporating through Hawking radiation, it doesn't vanish, it rebounds as a white hole, recycling its energy back into the cosmos. Imagine a dying star collapsing into a black hole, only to re-emerge millions of years later as a luminous fountain. If true, it would mean the universe has a hidden recycling program, turning voids into sources and death into rebirth. Whether white holes exist or not, their theoretical existence forces us to confront the fluidity of nothingness. The same equations that describe black holes crushing emptiness also allow for their radiant opposites, proving that the void isn't just one thing. It's a spectrum of possibilities, some dark, some dazzling. And if we ever did find proof of a white hole, it wouldn't just rewrite astronomy textbooks. It would reveal that the universe's emptiest places are also its most creative, hiding engines of renewal in the unlikeliest corners of the cosmos. What if the void between galaxies isn't just empty space but a cosmic shoreline, lapping against the edges of other universes? This isn't science fiction. It's the heart of multiverse theory, where our entire cosmos might be a single bubble floating in an infinite ocean of others, each with its own laws of physics, its own history, even its own version of you. The idea sounds fantastical, but it emerges from some of the most rigorous mathematics in physics, suggesting that what we call nothing could be the scaffolding for realities beyond imagination. Take cosmic inflation, the theory that our universe expanded exponentially in its first moments. Some models suggest this expansion never truly stopped, it just paused in our pocket of space. Elsewhere, new universes might be bubbling up endlessly, like boiling water spawning steam pockets. Each one could have different fundamental constants, a universe where gravity is stronger, light slower, or where atoms never formed at all. The void between them wouldn't be empty, it'd be a frothing quantum foam, birthing new realities like bubbles in champagne. String theory adds another layer. If the extra dimensions it proposes are real, our universe might be a three-dimensional membrane floating in higher dimensional space, like a sheet of paper in a vast stack. Other brain worlds could drift just millimeters away in a dimension we can't perceive, their gravity subtly tugging at ours. Suddenly, dark matter's mystery takes on a new twist. Could it be the gravitational shadow of a neighboring universe brushing against ours? Then there's the quantum multiverse. Every time a particle faces a choice like whether to spin left or right, some interpretations suggest the universe splits, creating parallel timelines. In one branch, you're watching this video, in another, you clicked away. These alternate realities aren't far off in space, they're layered atop ours, separated by probabilities rather than distance. The void becomes a hall of mirrors, reflecting every possible outcome of every quantum event since the Big Bang. Critics argue these ideas are untestable, more philosophy than science. But some physicists are devising clever ways to hunt for clues. If our universe collided with another long ago, the cosmic microwave background might bear scars from the impact, like a dent in a car fender hinting at an old accident. Others search for anomalies in gravity's strength or light's behavior that could betray leakage from adjacent dimensions. What's breathtaking is how these theories reframe emptiness. The void isn't a dead end. It's a frontier, perhaps teeming with other worlds. And if the multiverse is real, the most profound truth might be this: in the grand scheme of things, our universe's vastness is just a speck in something infinitely larger. The night sky's darkness isn't the absence of light, it's the curtain-hiding stages we've yet to see. Einstein's cosmological constant began as a desperate fix, a mathematical fudge factor scribbled into his equations of general relativity to keep the universe static. In 1917, the prevailing belief was that the cosmos stood still, neither expanding nor contracting. But Einstein's own equations predicted a dynamic universe, one that should either collapse under gravity or fly apart. Unwilling to challenge the astronomical dogma of his time, he inserted this constant as a repulsive force to balance gravity's pull, a cosmic push that kept everything perfectly, artificially frozen. Years later, when Edwin Hubble proved the universe was expanding, Einstein dismissed the constant as his greatest blunder, a mistake born of stubbornness. Yet in a twist worthy of Shakespeare, modern cosmology suggests he might have been right all along just for the wrong reasons. That discarded constant now looks eerily similar to dark energy, the mysterious force accelerating the universe's expansion. The numbers even align. The energy density of empty space calculated from quantum field theory matches the observed effects of dark energy to within an order of magnitude. It's as if Einstein accidentally painted a bullseye on a target no one knew existed, then walked away without realizing he'd hit it. What's fascinating is how the cosmological constant reflects the tension between theory and observation. Einstein initially rejected it because it felt unnatural. Why should empty space contain energy? But quantum mechanics later revealed that vacuums do seethe with energy. Virtual particles, zero-point fluctuations, all the quantum chaos we've explored suggests that nothing is inherently active. The cosmological constant, once seen as an arbitrary fix, now seems like an inevitable feature of a universe where emptiness isn't empty at all. The real irony: Einstein's blunder wasn't the constant itself, but his refusal to trust his equations. Had he embraced their prediction of an expanding universe, he might have anticipated Hubble's discovery by decades. Instead, his self-doubt became a cautionary tale for scientists. Sometimes the math knows things we don't. Today, the cosmological constant is central to the lambda-CDM model, our best map of the universe's evolution. It accounts for nearly 70% of the cosmos's energy budget, dwarfing everything made of atoms. But the story isn't over. The constant's predicted value from quantum theory is a staggering 120 orders of magnitude larger than what we observe, a discrepancy so vast it's been called the worst theoretical prediction in the history of physics. This mismatch hints that we're still missing something profound. Maybe dark energy isn't a constant at all, but a field that evolves over time. Or perhaps it's a sign of undiscovered physics, a clue that relativity and quantum mechanics need reconciliation. Einstein's journey with the cosmological constant mirrors science itself, a dance of intuition, error, and eventual revelation. What began as a fudge factor now underpins our understanding of cosmic acceleration, a reminder that even mistakes can light the path forward. The universe, it seems, has a sense of humor. The term Einstein crossed out may be the very key to unlocking its deepest secrets. Picture a sphere of darkness so vast it could swallow thousands of galaxies whole, yet inside, there's almost nothing. This is the Boötes Void, a cosmic desert spanning 330 million light-years where the usual glittering tapestry of stars and galaxies gives way to eerie emptiness. If you were to teleport to its center, the night sky would appear nearly black, with perhaps just a handful of faint galaxies visible to the naked eye. It's as if someone took an eraser to the universe, scrubbing away matter on a scale that defies comprehension. What could carve such a void? Astronomers first stumbled upon this anomaly in the 1980s while mapping galaxy distributions, expecting space to be relatively evenly populated. Instead, they found this staggering gap in the constellation Boötes, so large it challenges our understanding of cosmic structure. One theory suggests it's a remnant of the early universe, where density fluctuations left some regions devoid of matter. Imagine blowing soap bubbles most cluster together, but occasionally you get a lone, giant bubble floating apart. The Boötes Void might be that bubble, a fluke of inflation frozen in time. But there's a twist. The void isn't completely empty. Scattered galaxies do lurk within it, like lone islands in an ocean of nothingness. These outliers might hold clues to the void's origins. Some researchers propose that dark energy, the same force accelerating the universe's expansion, could have stretched this region faster than matter could keep up, leaving galaxies stranded. Others speculate that smaller voids merged over billions of years, like raindrops combining into a lake, creating this colossal emptiness, the most tantalizing possibility. The Boötes Void could be evidence of something far stranger, an ancient collision with another universe. In certain multiverse theories, our cosmos might have bumped into a neighboring one long ago, the gravitational recoil clearing out matter like a cosmic wrecking ball. While this remains speculative, it underscores how even the emptiest corners of space might whisper secrets about reality's deepest layers. Studying the void isn't just about solving a cosmic mystery. It's a stress test for our models of the universe. If voids this large shouldn't exist according to standard cosmology, what does that say about our theories? Every galaxy missing from the Boötes Void is a question mark, challenging us to rethink how structure forms in the cosmos. So the next time you gaze at the night sky, remember, the darkness between stars isn't uniform. Some patches are emptier than others, and in those voids lie puzzles that could reshape our understanding of everything. The Boötes Void isn't just an absence, it's a mirror reflecting how much we have yet to learn. Quantum entanglement is the universe's most baffling magic trick, a phenomenon so strange even Einstein called it spooky action at a distance. Imagine two particles born together, then flung to opposite ends of the galaxy. Change the spin of one and the other instantly responds, as if they're sharing a hidden conversation faster than light. This isn't telepathy, it's hard science, and it shatters our classical intuition about how emptiness works. If particles can whisper across cosmic voids without any detectable signal, what does that say about the space between them? The math behind entanglement is elegant but unsettling. When particles become entangled, they stop being independent objects and instead exist as a single quantum state. Measuring one automatically determines the properties of the other, no matter how far apart they are. It's like flipping a coin in New York and watching its twin in Tokyo land on the same side every single time. Experiments have confirmed this at distances exceeding 1,200 kilometers, with photons beamed between satellites and ground stations. The results are unambiguous. The universe doesn't care about separation when it comes to quantum connections. What makes this truly revolutionary is how it challenges the idea of empty space as a passive backdrop. Entanglement suggests that the void might be threaded with invisible links, a cosmic web of relationships that transcend distance. Some theories propose that space-time itself emerges from these quantum connections, like a 3D hologram projected from entangled information at the universe's edges. Others speculate that black holes could be entanglement factories, They're event horizons tying particles together in ways we're just beginning to grasp. The implications ripple beyond theory. Quantum encryption already uses entanglement to create unbreakable codes. If a hacker tries to intercept the signal, the entanglement breaks, alerting the users. Future quantum networks might span continents, with entangled photons enabling instant, secure communication. And if we ever crack the mystery of how entanglement truly works, it could rewrite our understanding of causality, proving that the universe's building blocks don't play by the rules we thought they did. Yet for all its weirdness, entanglement offers a profound insight. The cosmos might be far more interconnected than it appears. Those vast stretches of nothingness between stars could be humming with quantum threads, stitching reality together in ways we're only starting to perceive. So the next time you hear that space is empty, remember, it's not just vacuum. It's a stage where particles dance in perfect, inexplicable sync, no matter how far apart they roam. Imagine the universe as a pot of water on the verge of boiling, calm on the surface, but beneath, tiny bubbles form and pop in a chaotic dance. Now, what if space itself could bubble in the same way, with fleeting pockets of reality where the laws of physics rewrite themselves? This isn't just a thought experiment. Some of the most cutting-edge theories in cosmology suggest that the vacuum of space might spontaneously spawn microscopic universes, each with its own rules, hidden within the void of our own. The idea hinges on a peculiar property of quantum fields, the invisible energy landscapes that govern how particles behave. These fields aren't static, they fluctuate constantly, like waves on an ocean. Most of the time, these ripples average out, leaving the fabric of reality intact. But under extreme conditions, a quantum field might tunnel into a lower energy state, creating a bubble where physics operates differently. Picture a single drop of ink spreading through water, only instead of color, it carries an entirely new set of natural laws. This bubble would expand at the speed of light, rewriting everything in its path. What's truly wild is that these bubbles could become self-contained universes. If one formed with just the right conditions, it might inflate rapidly, driven by its own version of dark energy, a process eerily similar to the Big Bang that birthed our cosmos. In this scenario, our universe could be someone else's vacuum bubble, a cosmic Russian nesting doll where every void contains the seeds of new realities. Some physicists even speculate that the multiverse isn't just a collection of distant parallel worlds, but a frothing sea of these bubble universes, each born from quantum fluctuations in the empty space of a parent universe. The implications are staggering. If vacuum bubbles exist, they could explain why our universe seems so finely tuned for life. Most bubbles might collapse instantly or spawn hostile physics where atoms can't form. But occasionally, by sheer chance, one could stabilize into a universe like ours, a cosmic lottery winner where the constants align just right. It's a twist on the anthropic principle. We don't live in a special universe. We live in one of the rare bubbles where life was possible at all. Of course, detecting these bubbles is another matter. If one formed far away, we'd never know until its boundary reached us, and by then it'd be too late. Some theories suggest that high-energy particle collisions could, in principle, create microscopic bubbles, though the energy required is far beyond our current technology. Others look for subtle anomalies in the cosmic microwave background, hunting for fingerprints of long-ago collisions between our universe and a neighboring bubble. Yet, even if we never find direct evidence, the idea reshapes how we see the void. Emptiness isn't just a blank canvas, it's a crucible endlessly churning out possibilities. Every cubic centimeter of space could be a potential universe in waiting, a reminder that the cosmos thrives on transformation. So the next time you hear that space is mostly nothing, remember, it might be the most creative nothing there is. What if everything you see around you, the depth of space, the vastness of galaxies, even the screen you're staring at right now, is nothing more than an elaborate illusion? A cosmic trick of the light. That's the radical claim of the holographic principle, a theory suggesting our three-dimensional universe might be a projection from a two-dimensional surface, like a movie playing on the walls of reality itself. At first glance, it sounds like science fiction, but this idea emerges from some of the most rigorous physics of our time, bridging black holes, quantum mechanics, and the very nature of emptiness. The story begins with an unexpected discovery about black holes. In the 1970s, physicist Jacob Bekenstein calculated that the entropy, a measure of disorder, of a black hole isn't proportional to its volume as you'd expect, but to the area of its event horizon. It's as if all the information about what falls into a black hole gets smeared across its surface, not stored inside. This odd finding planted the seed for a revolutionary idea. What if all the information in the universe works this way, that the three-dimensional world we experience is just a hologram encoded on a distant two-dimensional boundary? Fast forward to the 1990s, when physicist Leonard Susskind and others formalized this into the holographic principle. The math suggests that the information needed to describe every particle, every force, every ripple of space-time in our universe could fit on a thin sheet surrounding it, like the label on a soda can containing the entire drink's ingredients. This doesn't mean we're living in a simulation. It's deeper than that. The universe might fundamentally be its boundary, with our 3D reality emerging from interactions on that edge, the way a 2D computer screen can create the illusion of depth when playing a video game. Here's where it gets even stranger. The holographic principle implies that space isn't smooth and continuous, as Einstein imagined, but pixelated at the tiniest scales. Just as a digital photo breaks down into blurry squares if you zoom in too far, spacetime itself might dissolve into indivisible bits at the Planck length, a scale a billion trillion times smaller than an atom. In this view, the void isn't empty, it's a seething network of information, a cosmic chessboard where every move shapes the reality we perceive. But how could a flat surface create the richness of 3D experience? Think of a hologram on your credit card. Shine light on its 2D surface, and a 3D image appears. The holographic principle proposes that the universe works similarly, with gravity and dimension arising from quantum interactions on a distant membrane. Even your sense of free will might be part of the illusion, a consequence of deeper, deterministic laws playing out on that boundary. The implications are staggering. If the holographic principle is correct, it would mean black holes don't destroy information but store it like celestial hard drives. Dark energy could be a side effect of the universe's pixel count, increasing as space expands. And those quantum entanglements we discussed earlier, they might be threads stitching the hologram together, connecting points that seem separate in 3D but are adjacent in the 2D code. Of course, not everyone's convinced. Testing the holographic principle is notoriously difficult. It's like trying to prove the air is made of molecules by staring at the wind. Yet experiments with ultra-precise lasers and particle colliders are hunting for signs of spacetime's pixelation, while theorists explore how holography could unify gravity and quantum mechanics. Already, it's reshaped how we think about emptiness, suggesting that the void isn't just full of secrets, it might be the secret, a flat canvas painting its own masterpiece in 3 dimensions. So the next time you reach out to touch something solid, remember, you might be feeling a shadow of something far more profound. The universe's truest self could lie not in its depth, but on its edges, a cosmic whisper reminding us that reality is never what it seems. Right now, as you watch this, an invisible storm is raging through your body. Trillions of ghostly particles called neutrinos, each smaller than an atom, passing through you at nearly the speed of light without leaving a trace. These cosmic phantoms are born in the hearts of stars, forged in supernova explosions, and blasted across the universe by black holes, yet they slip through planets like sunlight through glass. If the void of space has a hidden pulse, neutrinos are its heartbeat, threading through the emptiness with stories we're only beginning to decipher. What makes neutrinos so baffling is how little they care about the world of matter. Unlike electrons or protons, they carry no electric charge, barely interact with gravity, and can sail through a light year of solid lead without slowing down. Detecting them is like trying to catch smoke with your bare hands, a challenge so immense that early physicists assumed they'd never be measured at all. Yet in the 1950s, scientists built tanks deep underground, filled with cleaning fluid of all things, and waited. After years of patience, they spotted the occasional flash of light, proof that a neutrino had, against all odds, bumped into an atom. It was like hearing a whisper in a hurricane, but here's where neutrinos get even weirder. As they travel, they shape-shift between three different flavors: electron, muon, and tau, oscillating in a quantum dance that implies they have mass, however tiny. This discovery upended the standard model of physics, revealing gaps in our understanding of the universe's basic building blocks. Even more intriguing, neutrinos might be their own antiparticles, a property that could explain why the universe contains more matter than antimatter, why we exist at all. Their journey through the cosmos is no less extraordinary. Some neutrinos in your body right now are relics from the Big Bang, older than atoms themselves. Others were spat out by the sun's fusion furnace 8 minutes ago, while a handful might have traveled for billions of years after escaping the collapse of a dying star. In 2013, the ice cube detector in Antarctica caught a neutrino from a blazar, a supermassive black hole spearing the cosmos with jets of energy 4 billion light-years away. That single particle carried evidence of physics at energies far beyond anything we can recreate on Earth. So what do these phantoms tell us about the void? For one, they prove that emptiness is anything but sterile. Neutrinos fill space in unimaginable numbers, a cosmic fog so dense that if you could see them, the night sky would glow. They're also a reminder that the universe communicates in ways we're only starting to grasp, not just with light and gravity, but with particles so aloof they barely acknowledge reality's rules. Some theories even suggest neutrinos could be entangled with dark matter, their subtle mass sculpting the invisible web that holds galaxies together. The next time you look up at the stars, remember, you're not just an observer, you're a witness to an invisible river, a current of ghostly messengers linking you to the most violent and beautiful corners of the cosmos. And as we build ever more sensitive detectors in abandoned mines, under Antarctic ice, even on the ocean floor, we're not just chasing particles, we're learning to listen to the void's quietest whispers, one neutrino at a time. Deep in the vast emptiness between galaxies, something is pulling. Across hundreds of millions of light-years, entire galaxy clusters, including our own Milky Way, are being dragged toward an unseen force with the mass of tens of thousands of Milky Ways combined. Astronomers call this cosmic enigma the Great Attractor, and its existence turns our understanding of voids upside down. How can so much mass hide in what appears to be nothingness? The story begins in the 1970s, when astronomers mapping the universe's large-scale structure noticed something peculiar. Galaxies in our local supercluster weren't just drifting apart with the universe's expansion. They were all streaming toward a single point in the constellation Centaurus, moving at over 600 kilometers per second. The culprit, a gravitational anomaly so powerful it bends the paths of galaxies like a cosmic whirlpool. Yet when telescopes pointed toward that patch of sky, they found almost nothing. Just a sparse region known as the zone of avoidance, where dust from our own galaxy's plane obscures the view beyond. Here's where it gets stranger. Modern surveys piercing through that dust veil revealed the Great Attractor isn't the ultimate source of the pull. It's merely a waypoint on a far grander journey. Our entire local universe, including the Great Attractor itself, is being towed towards something even more massive and distant: the Shapley supercluster, a staggering concentration of matter containing nearly 10,000 galaxy clusters. This cosmic tug-of-war suggests that what we once thought was emptiness is actually a complex web of invisible mass, with gravity's tendrils reaching across voids we'd assumed were barren. The Great Attractor forces us to confront two radical possibilities. First, that the universe's empty regions might be filled with dark matter in configurations we don't yet understand, perhaps vast halos or filaments weaving between galaxies. Second, that our vantage point inside the Milky Way's dusty disk has left us blind to major structures hiding just beyond our line of sight. It's like living in a valley and assuming the entire world is flat, unaware of the mountain ranges obscured by fog. Recent observations from X-ray telescopes and infrared surveys are finally lifting that fog. They've uncovered galaxy clusters like Norma Cluster at the Great Attractor's heart, along with sprawling superstructures of hot gas, hints that what looks like a void is actually a crowded crossroads in the cosmic highway. Yet even these discoveries account for less than half the gravitational pull we observe, the rest still a mystery, possibly tied to dark energy's influence or undiscovered physics governing how matter clusters across the largest scales. What makes the Great Attractor so compelling isn't just its hidden mass, it's what it represents. The universe doesn't do true emptiness. Even the darkest voids hum with gravitational potential, sculpting the paths of galaxies over eons. And as we peer deeper into these apparent nothingnesses, we're reminded that the cosmos always has another secret waiting where we least expect it. Zoom in far enough, past atoms, past quarks, down to scales a billion times smaller than anything we can directly observe, and the smooth, predictable fabric of space and time begins to churn. Here, in the realm of quantum foam, the universe loses all semblance of order. Space isn't flat or empty. It's a seething, bubbling cauldron where tiny pockets of reality twist, stretch, and dissolve in a frenzied dance. Imagine the surface of a stormy ocean, but instead of water, it's space-time itself that's writhing, with fleeting wormholes, miniature black holes, and even entire baby universes popping in and out of existence too quickly to measure. This isn't poetic exaggeration, it's the prediction of quantum gravity theories trying to reconcile Einstein's relativity with the chaos of the quantum world. The idea of quantum foam was first proposed by physicist John Wheeler in the 1950s, but its roots go deeper. At the Planck scale, a distance so small it would take 10 trillion of these lengths to cross a single atom. The energy fluctuations become so violent that space-time can no longer hold its shape. Gravity, normally the weakest of forces, dominates here, warping the fabric of reality into knots and tangles. It's like looking at a sheet of paper through a microscope. What seemed smooth is actually a tangled mesh of fibers, constantly shifting. In this microscopic frenzy, the very concepts of here and now break down, cause and effect blur. A particle might momentarily exist in two places at once, or tunnel through a wormhole thinner than a quark before snapping back into place. What does this mean for our understanding of nothingness? For one, it suggests that the vacuum of space is anything but inert. Even if you could remove every atom, every photon, every trace of matter and energy, the void would still crackle with this quantum turbulence. The foam isn't made of something, it is space-time itself, twisted into shapes we can't yet describe. Some theories even propose that dark energy, the force accelerating the universe's expansion, might emerge from this froth, like bubbles in a boiling pot pushing against the edges of reality. The wildest implication, quantum foam could be the key to unifying physics' greatest theories. Einstein's relativity paints spacetime as a smooth, bendable sheet, while quantum mechanics insists everything is discrete and jumpy. The foam might be where these two pictures merge, a realm where spacetime becomes granular, a pixelated canvas underlying the smooth universe we perceive. Picture a digital image, zoom out and it looks seamless, zoom in and you see the pixels. Quantum foam suggests reality works the same way, with spacetime's pixels flickering in and out of existence at scales we're only beginning to fathom. Of course, detecting this foam directly is nearly impossible. Its features are vanishingly small and fleeting. But scientists aren't giving up. Some hunt for its fingerprints in the light from distant gamma-ray bursts, looking for subtle delays that might betray spacetime's lumpy texture. Others probe the behavior of ultra-sensitive atomic clocks, watching for tiny inconsistencies that could reveal the foam's turbulence. Even gravitational wave detectors like LIGO might one day catch echoes of microscopic wormholes snapping shut in the cosmic background. So the next time you hear that space is empty, remember, it's only empty in the way a thundercloud is just air. Beneath the surface, forces are at work that rewrite the rules of existence moment by moment. Quantum foam doesn't just redefine nothingness, it turns the void into the universe's most creative workshop, where reality itself is continually torn apart and stitched back together. Energy isn't always a force pushing things forward, sometimes it pulls. Imagine a form of energy so strange it doesn't just fade to zero but dips below, creating a kind of cosmic tug that warps spacetime in ways gravity never could. This is negative energy, a theoretical wildcard that could rewrite the rules of the void. While it sounds like science fiction, the math suggests it might be real, lurking in the quantum shadows of empty space. The concept emerges from Einstein's equations, where energy and spacetime curvature are inseparable. Normally, positive energy, like mass or light, bends spacetime inward, creating the gravity we know. But flip the sign and something extraordinary happens. Spacetime repels instead of attracts. Picture a rubber sheet stretched taut, then suddenly pushing upward against objects placed on it. Negative energy could make that happen, turning the fabric of reality into an anti-gravity trampoline. Where might such energy hide? Quantum field theory offers a clue. The vacuum isn't truly empty. It's a storm of virtual particles borrowing energy from the void. Sometimes these loans create temporary deficits, regions where energy dips below zero. It's like balancing your checkbook by momentarily overdrawing, then repaying the debt before the universe notices. These fleeting negative energy fluctuations might be the key to phenomena like wormholes, hypothetical shortcuts through spacetime. To stabilize a wormhole's throat and prevent it from collapsing, you'd need something to prop it open against gravity's crush. Negative energy could be that cosmic scaffolding, creating a repulsive force to counterbalance the squeeze. But the implications go far beyond wormholes. If negative energy exists, it could explain dark energy's accelerating push on the universe. Some models suggest dark energy might be a dynamic field whose pressure occasionally swings negative, driving expansion in fits and starts. Even black holes might harbor traces of it near their event horizons, where quantum effects twist the usual rules. The catch: negative energy defies our intuitive grasp of physics. It challenges the weak energy condition. a long-held assumption that energy density can't be negative for observers moving at sublight speeds. Yet experiments like the Casimir Effect, where the vacuum's energy density drops between closely spaced plates, hint that nature might allow exceptions. Creating usable amounts of negative energy remains speculative, but labs have manipulated quantum systems to produce microscopic pockets of it, like bending a spoon's handle without breaking the bowl. Whether negative energy is a cosmic quirk or a fundamental feature of the void, its possibility forces us to rethink what nothing can do. The universe's emptiest places might not just hide energy, they could harbor forces that invert reality itself. And if we ever learn to harness them, the void might become the ultimate source of surprises. Imagine folding a piece of paper so two distant dots touch, then punching a hole through where they meet. That's the essence of a wormhole, a hypothetical tunnel through space-time that could turn a billion light-year journey into a stroll across the cosmic backyard. While they sound like pure science fiction, wormholes emerge straight from Einstein's equations of general relativity, where the fabric of space and time bends so severely that two distant points kiss. But here's the catch. These cosmic shortcuts don't just connect places, they rewrite the rules of emptiness itself. The math behind wormholes reveals something startling. To stay open, these tunnels would need walls made of exotic matter with negative energy, stuff that repels rather than attracts. Remember those quantum fluctuations we discussed earlier, where particles borrow energy from the void? Under extreme conditions, this quantum generosity might stretch space-time into a stable bridge. Picture a soap bubble's delicate film, but instead of soap, it's woven from the universe's underlying tension, a tension that, if tweaked just right, could stitch distant regions together. But why haven't we found one? Wormholes, if they exist, would likely be microscopic, snapping shut faster than they form thanks to gravity's relentless crush. Keeping one open would require engineering on a godlike scale, arranging negative energy like scaffolding in a black hole's throat or manipulating cosmic strings, hypothetical defects in spacetime left over from the Big Bang. Even then, passing through might be lethal. Some models suggest wormholes would amplify radiation to deadly levels, turning any traveler into quantum soup before they reach the other side. Yet the possibilities tantalize. A stable wormhole could link not just space but time, creating closed time-like curves where the past and future loop back on themselves. It's the ultimate paradox, stepping into a void only to emerge somewhere, or someone else entirely. Recent simulations even suggest wormholes might mimic black holes so closely that we've already been observing them without realizing it. The dark shadows at galaxies' hearts could be portals in disguise, their event horizons masking tunnels to elsewhere. The real magic lies in what wormholes imply about the void. Far from passive emptiness, space might be a labyrinth of hidden connections, folded in ways we're only beginning to map. Whether these tunnels exist or not, their theoretical existence proves one thing: the universe's blankest canvases might be its most intricate masterpieces, waiting for us to see beyond the illusion of nothingness. Einstein never liked the idea that reality might depend on how we look at it. In 1935, he teamed up with physicists Boris Podolsky and Nathan Rosen to expose what they saw as a fatal flaw in quantum mechanics, a thought experiment so unsettling it became known as the Fermi Paradox. At its heart was a simple but explosive question: can two particles communicate faster than light, or does the universe contain hidden layers we can't yet see? The answer would rewrite our understanding of emptiness itself. Picture two entangled electrons born from the same atom, then flung to opposite ends of the galaxy. Measure one's spin as up, and quantum theory insists its twin instantly becomes down, no matter the distance. To Einstein, this spooky action at a distance was absurd. It violated relativity's cosmic speed limit, the idea that nothing can outtrace light. He argued there must be hidden variables, unseen properties predetermined at the moment of entanglement, making the particle's behavior seem coordinated when it was really just following a script written long ago. In this view, the void between them would be truly empty, with no secret signals racing through the dark, but quantum mechanics doubled down on the weirdness. Decades later, physicist John Bell devised a way to test Einstein's hidden variables against quantum theory's wilder claims. His equations showed that if hidden variables existed, entangled particles would correlate in one way. If quantum mechanics was right, they'd correlate differently. When experiments finally ran the numbers first in the 1970s, and with increasing precision since, the results were unmistakable. Particles defied Einstein's local realism. Their connection wasn't prearranged, it was instantaneous, as if space between them didn't exist. This leaves us with a cosmic riddle. If entanglement bridges voids faster than light, what does that say about the fabric of space? One radical interpretation suggests that separation itself might be an illusion, that at some fundamental level, every particle in the universe is subtly linked, and the void is just a stage where these connections play out. It's as if reality is a vast hologram with information about every particle encoded at its edges, making the space between them a kind of cosmic sleight of hand. Others propose that entanglement reveals extra dimensions, threads woven through higher spaces we can't perceive. Imagine ants crawling on a sheet of paper, unaware that a second page lies millimeters above them in the third dimension. From their flat perspective, a message appearing simultaneously on both sheets would seem magical, but to us, it's just a matter of folding the paper. Could entanglement work the same way, with particles touching through unseen folds in spacetime? The most unsettling possibility, that the void isn't a passive backdrop but an active participant in reality's construction. Quantum fields permeating empty space might mediate these instantaneous links, meaning what we call nothing is actually a dynamic network, humming with invisible handshakes between particles. It's a vision that would have horrified Einstein, one where the universe isn't just stranger than we imagined, but stranger than we can imagine, with emptiness itself as the conductor of its deepest symphonies. So the next time you hear that space is mostly void, remember, that void might be the most crowded place of all, threaded with connections that defy time and distance. The Fermi Paradox didn't just challenge quantum mechanics, it revealed that the emptiest reaches of the cosmos could be where reality's truest nature hides. Picture a cosmic bank where the universe lends energy with no paperwork, just an unbreakable rule that every loan must be repaid instantly. This is the bizarre reality of virtual particles, quantum mechanics' way of turning empty space into a bustling marketplace of fleeting existence. According to Heisenberg's uncertainty principle, the vacuum isn't just allowed to briefly violate energy conservation, it's required to. Particles and their antimatter twins materialize from nothing, dance for fractions of a nanosecond, then vanish like mirages, all without leaving a trace in the ledger. It's as if the void is a simmering pot with bubbles of reality constantly forming and popping on its surface. These ephemeral particles aren't just mathematical quirks, they leave fingerprints everywhere. The Casimir Effect, where metal plates in a vacuum mysteriously attract each other, happens because virtual particles outside the plates exert more pressure than those confined between them. It's like being in a crowded elevator where people pushing in from the hallway create a squeeze no one can see. Even the electrons orbiting atoms feel their presence. A hydrogen atom's electron isn't just interacting with its proton. It's constantly buffeted by virtual photons and other particles flickering in and out around it, subtly altering its energy levels in ways precise enough to measure with lasers. But the real cosmic twist, virtual particles might be responsible for the universe's very existence. During inflation, the explosive expansion moments after the Big Bang, quantum fluctuations in this seething vacuum were stretched to astronomical sizes, becoming the seeds for galaxies. Those microscopic hiccups in nothingness now loom overhead as galaxy clusters, their patterns mirroring the quantum foam's chaos. Even black holes pay tribute to the void's creativity through Hawking radiation, where virtual particles near the event horizon get torn apart, one falling in while the other escapes as real energy. The whole slowly evaporates, its mass leaking away thanks to particles that technically never existed long enough to be counted. What's truly humbling is how this reshapes our definition of empty. A perfect vacuum, stripped of all matter and light, still crackles with these quantum transactions, a background static of existence so relentless it's been called the zero-point energy of universe. Some calculations suggest the energy density in a coffee cup's worth of pure vacuum could boil Earth's oceans, if only we knew how to extract it. That's the irony. The void isn't just full of surprises. It's the most generous lender in existence, if you don't mind the repayment terms being instantaneous. So the next time you think of space as a void, remember, it's more like a cosmic casino where particles place infinite bets, knowing the house always wins, but not before reshaping reality with every roll of the quantum dice. The Big Bang didn't just create the universe, it rewrote the very meaning of nothing. Picture a singularity so dense that all the energy, matter, and space we see today was compressed into a volume smaller than an atom. No stars, no galaxies, not even the vacuum we call empty space, just pure potential, a cosmic seed waiting to unfurl. But here's the twist. This wasn't an explosion into space. It was the birth of space itself, a moment when time, gravity, and the void all flickered into existence from a state we still struggle to define. What came before? The honest answer is we don't know. Our physics breaks down at the singularity, where the equations of general relativity and quantum mechanics collide in a storm of infinities. Some theories suggest there was no before, that time itself began with the Big Bang, making the question meaningless. Others propose a cyclical universe, where our cosmos is one bubble in an endless cycle of expansion and collapse. Then there's the multiverse hypothesis, where our Big Bang was just one spark in an infinite sea of universes, each with its own laws. But one thing's certain, the nothingness preceding the Big Bang wasn't empty. It was a canvas without form, a realm where the rules of cause and effect hadn't yet been written. The real magic lies in how this primordial void transformed into everything. In the first trillionth of a second, a phenomenon called inflation stretched spacetime faster than light, smoothing it into the vast expanse we see today. Quantum fluctuations, those tiny ripples in the fabric of nothingness, were magnified to cosmic scales, becoming the blueprints for galaxies. It's like blowing up a balloon with microscopic wrinkles, inflated enough, and those wrinkles become mountain ranges. The same quantum chaos that creates virtual particles in a lab vacuum once sculpted the largest structures in existence. But the most haunting question remains: why was there something instead of nothing at all? Some physicists point to the laws of quantum mechanics, where particles appear spontaneously if the energy balance is zero. In this view, the universe might be the ultimate free lunch, a fluctuation in a deeper void where positive and negative energies cancel out. Others speculate that the conditions for existence are inevitable, that given enough time, whatever that means beyond our universe, a cosmos like ours had to emerge. What's undeniable is this: the Big Bang didn't happen in the void, it was the void waking up. The darkness we see between stars isn't just leftover emptiness. It's the echo of that first transformation, the moment when nothingness became everything. And as we peer deeper into the cosmic microwave background, the afterglow of that primordial fire, we're not just studying the past, we're staring into the face of the void itself, asking it to reveal how existence began. Imagine throwing a ball at a wall, only for it to vanish and reappear on the other side without breaking the surface. That's the essence of quantum tunneling, a phenomenon where particles bypass barriers they seemingly shouldn't be able to cross, like ghosts walking through walls. In the cosmic void, this isn't just a laboratory curiosity. It's a fundamental process shaping stars, atoms, and even the fate of the universe itself. At the heart of tunneling lies quantum mechanics' most radical idea. Particles aren't just tiny marbles but probability waves smeared across space. When a particle encounters a barrier, like an energy wall that classical physics says it can't surmount, its wave function doesn't abruptly stop. Instead, it tapers off exponentially, leaving a tiny but non-zero chance the particle will materialize on the far side. It's as if the void itself grants particles a cosmic loophole, letting them cheat their way past obstacles by borrowing uncertainty. This isn't theoretical. Without tunneling, the sun wouldn't shine. In its core, protons repel each other due to their positive charges, yet they fuse into helium to release energy. The reason: quantum tunneling allows them to momentarily skip through the electrostatic barrier, like thieves slipping past a laser security grid. The same process powers radioactive decay, where alpha particles tunnel out of atomic nuclei, and even your electronics, where electrons tunnel through microscopic gaps in transistors to keep your devices running. But tunneling's strangest implications emerge in the void of space. Black holes might exploit it to slowly leak Hawking radiation, while cosmic inflation, the universe's exponential early growth, could have been triggered by a quantum-triggered phase transition. Some theories even suggest entire universes might tunnel into existence from the quantum foam, bubbling up like droplets condensing in a cold glass. The deeper lesson: the void isn't just empty space, it's a realm where the impossible becomes routine, where particles rewrite the rules simply by refusing to accept no for an answer. And as we peer into the cosmos, we're not just observing distant objects, we're witnessing the quiet rebellion of reality against its own limits. At the heart of modern physics lies an embarrassing secret: our equations don't add up. When scientists calculate the energy of empty space using quantum theory, the numbers are off by a factor of 1 followed by 120 zeros, the worst mismatch in science history. But what if the void isn't broken? What if we're just missing half the pieces? Enter supersymmetry, a bold theory suggesting every known particle has a hidden twin, lurking unseen in the cosmic shadows. These ghostly partners could be the key to balancing the universe's books, transforming the void from a mathematical disaster into a harmonious equation. Supersymmetry, or SUSY for short, emerged in the 1970s as physicists grappled with strange patterns in particle behavior. The theory proposes an elegant swap. For every Fermion particles like electrons and quarks that make up matter, there's a boson force carrying particles like photons, and vice versa. Picture a cosmic mirror where every dancer has a partner, their steps perfectly synchronized across dimensions we can't yet perceive. These sparticles, superparticles, would be heavier than their twins, explaining why we've never spotted them. They'd require energies far beyond today's colliders to create. But SUSY isn't just about tidying up math. These hidden particles could solve multiple cosmic riddles at once. Dark matter, that invisible glue holding galaxies together. The lightest particle might be stable enough to fill that role, a WIMP weakly interacting massive particle that barely touches normal matter except through gravity. The Higgs boson's oddly low mass, particles could subtly cancel out quantum corrections that would otherwise make it impossibly heavy. Even the vacuum energy catastrophe, that gargantuan mismatch in void calculations, might resolve if particles' contributions neatly offset their twins, like balancing a seesaw with equal weights. The hunt for these phantoms has been relentless. The Large Hadron Collider has scoured collision debris for signs of particles, while deep underground detectors wait for a WIMP to bump into atomic nuclei. So far, silence, yet many theorists aren't ready to give up. Some versions of SUSY predict particles just beyond our current reach, their masses tweaked by hidden dimensions or other exotic physics. Others suggest we've been looking for the wrong signals. Perhaps particles decay too quickly to spot, leaving only faint energy fingerprints in their wake. Critics argue SUSY flexibility makes it unfalsifiable, a theory that can always shift goalposts to evade disproof, but its mathematical beauty keeps it alive. Like a master key, it elegantly unlocks problems from the hierarchy of particle masses to the unification of forces. Even if SUSY isn't nature's final answer, it's taught us to listen for symmetry's whisper in the void's chaos. Because sometimes the universe's deepest truths aren't found in what we see, but in the patterns hidden just beyond the light. The universe is unimaginably vast, billions of galaxies, each with billions of stars, countless planets orbiting in the so-called Goldilocks zone where life could thrive. With numbers like these, the cosmos should be teeming with civilizations, their signals buzzing across the void like interstellar radio stations. Yet when we listen, all we hear is silence. This eerie absence is the heart of the Fermi Paradox, a puzzle that forces us to confront what the emptiness of space might really mean. Consider the math for a moment. Even if only 1 in a million planets develops intelligent life, there should still be thousands, perhaps millions of advanced civilizations scattered across the Milky Way alone. Some should have colonized entire swaths of the galaxy by now, their presence as obvious as streetlights on a dark highway. So why haven't we found them? Where is everybody? One chilling possibility is that the void isn't just empty, it's deadly. The Great Filter theory suggests there's some catastrophic hurdle that prevents life from progressing beyond a certain point, a cosmic bottleneck that wipes out civilizations before they can spread. Maybe it's the inevitability of self-destruction, nuclear war, environmental collapse, or runaway artificial intelligence. Or perhaps it's something external, like gamma-ray bursts sterilizing planets at random. If this filter lies ahead of us, humanity's future could be bleak. But if we've already passed it, if we're among the rare exceptions, then the silence might mean we're alone in a graveyard. Then there's the zoo hypothesis, the idea that advanced civilizations are out there but deliberately avoiding contact, observing us like animals in a galactic nature preserve. It's a comforting thought, but it raises unsettling questions. Who gets to enforce such a policy across millennia? And what happens when humanity finally starts knocking on the door? Other explanations are less ominous but equally mind-bending. Maybe interstellar travel is fundamentally impossible, locked behind physics we don't yet understand. Or perhaps advanced civilizations transcend physical forms, uploading their minds into virtual realities or merging with AI, leaving the material universe behind. In that case, the void isn't empty, it's full of beings we simply can't perceive, like ants unaware of the internet buzzing overhead. The most humbling answer. We might be early. The universe is 13.8 billion years old, but it could exist for trillions more. Intelligent life might typically emerge far in the future when conditions are more stable. If so, we're like the first birds chirping at dawn, wondering why the forest is so quiet. Whatever the truth, the Fermi Paradox forces us to rethink our place in the cosmos. That silence isn't just absence, it's a mirror reflecting our deepest hopes and fears about what lies beyond. And as we keep listening to the void, we're not just searching for aliens. We're searching for clues about whether the universe is a place of possibility or a desert where life flickers briefly, then vanishes without a trace. Time doesn't tick at the same rate everywhere, not just in theory, but in practice. Near massive objects like black holes or neutron stars, gravity's grip is so strong that time slows to a crawl, an effect confirmed by atomic clocks on Earth's surface running slightly slower than those in orbit. But what about the opposite extreme? In the deepest cosmic voids, where matter is almost absent and gravity's pull is weakest, time doesn't just pass, it accelerates. The emptier the space, the faster the universe's clock ticks compared to denser regions. This isn't science fiction. It's a direct consequence of Einstein's general relativity, where space-time isn't just a stage, it's an active participant, bending and flexing under the weight of matter and energy. Picture two clocks, one placed in the heart of a galaxy cluster, surrounded by trillions of stars, and another adrift in the Boötes Void, where galaxies are scarce. Over billions of years, the void's clock would pull ahead, its seconds ticking slightly faster than its crowded counterpart. The difference might seem negligible, a few microseconds over a human lifetime, but across cosmic timescales, these gaps add up. A civilization born in a dense galactic hub might find its history unfolding in slow motion compared to neighbors in the void, their stars aging faster, their planets cooling sooner. It's as if the universe has built-in time zones, with emptiness acting as a temporal fast-forward button. Why does this happen? Gravity doesn't just bend space, it warps time. Where matter congregates, spacetime curves so intensely that light and time itself must take longer paths. But in voids where gravity's grip relaxes, spacetime flattens out, offering less resistance to time's flow. Think of it like hiking up a mountain versus strolling on a plain. The climb gravity slows you down, while the flat terrain emptiness lets you move freely. This effect, called gravitational time dilation, reveals a startling truth. Now is a local phenomenon. There's no universal clock ticking in sync across the cosmos, just a patchwork of timelines, each shaped by the void or the matter around it. The implications stretch beyond abstract physics. If we ever master interstellar travel, navigating these temporal tides will be crucial. A ship speeding through a void might return to find its homeworld aged centuries, a real-life twist on the twin paradox. Even our observations of distant galaxies are tinted by this effect. Light reaching us from clusters is redshifted not just by cosmic expansion, but by the extra time it spent crawling out of a deep gravitational well. The void, it turns out, isn't just empty space, it's a temporal highway where the universe's clock runs unchecked, revealing that time, like everything else, is shaped by the nothingness we so often overlook. Einstein's general relativity paints gravity as the curvature of spacetime, a smooth, geometric dance where planets and stars warp the cosmic fabric like weights on a trampoline. Meanwhile, quantum mechanics describes particles as discrete packets of energy, buzzing in a probabilistic frenzy where emptiness teems with virtual particles and uncertainty reigns. These two theories work flawlessly in their own domains, but when it comes to the void's deepest scales where spacetime itself might dissolve into a quantum foam, they clash violently, like two languages describing the same world with entirely incompatible grammars. Bridging this divide is the monumental challenge of quantum gravity, a theory that could finally reveal what the void truly is when no one's looking. The stakes couldn't be higher. Without quantum gravity, our understanding of the universe remains fractured. Black holes, for instance, are where both relativity and quantum mechanics scream for answers. Relativity says matter collapsing into a singularity should vanish from the universe, while quantum mechanics insists information can never be destroyed. Hawking radiation, the slow leak of energy from black holes, hints at a solution, but without a unified theory, it's like trying to assemble a puzzle with half the pieces glued together. Even the Big Bang's first moments are a blur. Did space-time emerge from a quantum fluctuation? Was there a before? These aren't just philosophical musings, they're gaps in the bedrock of reality itself. String theory is one audacious attempt to mend this rift. It proposes that particles aren't dots but tiny, vibrating strings, with their notes determining their properties. In this symphony of the cosmos, gravity emerges as just another vibration, harmonizing with the other forces. The math is elegant, but it comes with baggage, extra dimensions curled into spaces smaller than atoms, and a landscape of possible universes so vast it's hard to test. Yet, if correct, it would mean the void isn't empty at all. It's a multidimensional loom, weaving spacetime from threads we can't yet see. Loop quantum gravity takes a different approach. Instead of strings, it imagines spacetime as a network of interconnected loops, a cosmic mesh where even the tiniest volume can't be divided further. Picture the universe as a pixelated image, but where each pixel is a tiny, indivisible chunk of spacetime. This framework beautifully avoids singularities. Black holes become knots in the mesh, not infinite pits, but struggles to explain how smooth spacetime emerges from this granularity. Still, it offers a tantalizing vision, the void as a dynamic fabric, its threads tightening and loosening to create the forces we know. Then there's the wild card, emergent gravity. Some theorists suggest gravity isn't a fundamental force at all, but a side effect of entropy, the universe's natural tendency toward disorder. In this view, gravity is like the pressure in a gas, a collective behavior of deeper, unknown components. It's as if the void has a hidden layer, like the code running a video game, and gravity is just what happens when the program runs. This idea, though radical, could explain dark energy and dark matter without inventing new particles, framing them instead as artifacts of spacetime's underlying structure. The common thread, all these theories force us to rethink nothingness. Whether it's strings, loops, or holograms, they suggest the void is a construction site, humming with activity too subtle for our current tools to detect. And while we haven't yet found proof of any approach, the hunt itself is reshaping physics. Experiments like gravitational wave detectors and quantum entanglement tests are probing realms where quantum gravity's fingerprints might appear. Even failures are illuminating. Each dead end teaches us what the void isn't, narrowing the path to what it truly is. So while we lack a final theory, the quest for quantum gravity has already revealed something profound. The universe's emptiest places might be where its most creative work happens. Whether spacetime is woven, pixelated, or coded, one thing's clear: the void isn't passive. It's the stagehand behind reality's curtain, and we're just beginning to glimpse its hands at work. The next decade promises to peel back the void's deepest secrets like never before. Not with brute force, but with ingenious tools that listen, measure, and even taste the emptiness. Take NASA's upcoming Nancy Grace Roman Space Telescope, set to launch by 2027. Unlike Hubble or Webb, which focus on luminous objects, Roman is designed to map the dark cosmos, tracking how dark energy stretches voids over time by observing millions of galaxies. It's like watching invisible hands tug at the universe's fabric by measuring the wrinkles they leave behind. Meanwhile, the European Space Agency's Euclid mission is already scanning the sky for distortions in starlight caused by dark matter's gravitational grip, revealing how these unseen structures sculpt the voids between galaxies. But the revolution isn't just in space, it's in labs here on Earth. Quantum physicists are crafting experiments so precise they can weigh the void itself. At institutions like Fermilab and CERN, researchers are measuring the Casimir effect with nanometer-scale accuracy, probing whether quantum fluctuations behave differently in extreme environments. Some teams are even cooling atoms to near absolute zero, creating quantum vacuums where particles are stripped away entirely, leaving behind a pristine stage to study spacetime's fundamental noise. It's akin to silencing a crowded room to hear the faintest whisper, except the whisper might be the universe's quantum code. Then there's the audacious dream of harnessing the void. DARPA and private ventures are exploring zero-point energy not as sci-fi fuel, but as a way to manipulate quantum fields for propulsion. Imagine spacecraft pushing against the vacuum's seething energy like surfers riding quantum waves. Theoretical models suggest such engines could bypass the need for traditional fuel, though the energy thresholds remain daunting. More immediately, quantum entanglement experiments might soon enable void communication, using entangled particles to transmit information across space without signals, exploiting the universe's hidden connectivity. The boldest ideas, though, come from theorists. Some propose that future telescopes could detect primordial wormholes by their gravitational shadows, while others suggest hunting for bubble universes in the cosmic microwave background, scars from collisions with other realities. There's even talk of simulating alternate physics in lab-created vacuums, testing how different quantum rules might spawn universes with no dark energy or extra dimensions. What ties these quests together is a paradigm shift. We're no longer just observing the void, we're learning to converse with it, deciphering its quantum murmurs, mapping its invisible architecture, and perhaps one day rewriting its deepest rules. The greatest discoveries ahead won't just fill textbooks, they'll redefine what we consider possible at the frontier between something and nothing. The void has always been the universe's greatest illusion. What seems like nothing is actually everything. We've peeled back the cosmic curtain to reveal a hidden world where particles blink in and out of existence, where dark energy stretches the fabric of spacetime itself, and where the emptiest corners of space might hold the keys to parallel realities. This journey through the physics of nothingness has shown us that emptiness isn't passive. It's the stage where reality's most spectacular performances unfold. Consider how far we've come. Centuries ago, astronomers saw the blackness between stars as mere absence, a blank canvas waiting to be filled. Today, we know that canvas is alive with quantum foam, crackling with virtual particles that shape the very atoms in your body. The darkness between galaxies isn't just distance, it's a dynamic landscape where dark matter weaves invisible scaffolding and dark energy accelerates the cosmos toward an uncertain fate. Even black holes, those cosmic vacuum cleaners, leak secrets through Hawking radiation, proving that no void is truly silent. What's most extraordinary is how these discoveries redefine our place in the universe. That starless patch of sky you glanced at last night, it might contain more dark energy than all the visible stars combined, the empty space inside an atom. A whirlwind of quantum potential that makes matter possible. We're not just observers of this hidden realm, we're products of it. Every element in your body was forged in stellar furnaces, then scattered across the void by supernova, only to reassemble here now as conscious matter contemplating its own origins. The frontier of void physics promises even greater revelations, with telescopes like Roman and Euclid mapping dark energy's fingerprints. and quantum labs probing spacetime's pixelated nature, we're on the verge of breakthroughs that could rewrite physics textbooks. Maybe we'll find that vacuum decay is real or detect whispers from bubble universes. Perhaps we'll finally understand why the universe favors existence over true nothingness, whether it's inevitable math or cosmic luck. So the next time you gaze into the night sky, don't just see the stars, see the space between them, the vibrant, mysterious void that connects everything. It's not emptiness, it's the universe's heartbeat, the hidden script of reality waiting to be read. And as we keep exploring, remember, the greatest adventures aren't just in the light, but in deciphering the darkness. If this journey through the physics of nothingness sparked your curiosity, smash that like button and subscribe for more deep dives into the universe's wonders. Drop a comment below what cosmic mystery fascinates you most. Until next time, keep looking up and never stop wondering about the invisible forces shaping our extraordinary cosmos.